For this next lesson on composition, we're going to talk about the effect on composition of two functions and the domain. So what I hope you kind of started to see a glimpse of in our last lesson is that when you compose two functions, you get a new function. So f of g of x is a new function that's kind of this combination of our two functions. Same with g of f of x. And anytime we have a new function, we ask that question. What is this function's domain? So to walk us through it, I have kind of two examples that I want us to walk through. So I'm going to zoom in real clearly so you can see everything really well. So for the first example, we're dealing with two functions. F of x is the square root of x minus 2, and g of x is x squared minus 5. So let's find g of f of 3. So I'm never going to get tired of drawing this picture. And frankly, I think you should draw it too. So 3 gets passed through f. What does f do? F subtracts 2 from our input and then takes the square root. So 3 minus 2 is 1. The square root of 1 is 1. And then g acts on it. So what does g do? G squares its input and subtracts 5. So 1 squared minus 5 is negative 4. So g of f of 3 is negative 4. All right, cool. So now let's move on to b. So for b, 0 gets dropped into f. And f says, okay, cool, I'm going to subtract 2 from you and then take the square root. But what happens? Red lights, disaster, because when you go to subtract 2 from 0, you get negative 2, and the square root of negative 2 is not a real number, so we get this like total stop. It's almost like, you know, those red lights that flash in factories when there's an emergency. 0 is not in the domain of f. So 0 is never even going to make it out of f, let alone then something happens with g. 0 gets rejected by f and this whole composition stops. So what's really important here is g is a perfectly happy-go-lucky quadratic function. It takes anything as an input. It has an unrestricted domain. But before an input ever gets to see the inside of g, it has to pass through f first. And if an input is not in the domain of f, it's never going to even get to g. So when we're talking about the domain of the composition, we have to look at all of the stages of the process along the way. So now let's talk about the domain of g of f of x. So we're going to sort of use our lesson from part B here. And again, I'm going to draw this picture. So look, let's trace x's path as it goes first through f and then through g. So f says, hello, welcome. You can only come inside if you are in my domain. And what is my domain? Well, I am the square root of x minus 2, and I can only take square roots of non-negative numbers. So right off the bat, you have to be greater than or equal to 2. Period. If you are not greater than or equal to 2, you cannot pass, and your journey ends here. And x, if it succeeds, meaning if it is greater than or equal to 2, it is able to pass through f, it comes out as f of x, and now it moves on to g. So g has the same sort of interaction with its inputs. It says, hello, come in. You can only pass through me if you are in my domain. Except in this particular example, g is a quadratic function, x squared minus 5. It has no domain restrictions, so we can put here no domain restrictions, which means G does not impose any additional restrictions on its inputs that come through it. It doesn't mean that the x greater than or equal to 2 disappears. So if we trace x's journey through this path, we see, oh, well, x had to have been greater than 2. Otherwise, it would have never made it out of F. Once it makes it out of F, it's in the clear because anything can go through G. So the domain of G of F of X is all real numbers greater than or equal to 2. Now, a really interesting question that you might ask yourself is what would the domain of F of G of X be? But we'll talk about that later. Now let's actually find G of F of X, okay? So, and I don't mean like its domain, I mean actually what happens? What will X come out of first F, then G looking like? So it comes out of F as the square root of X minus 2. There we are. Okay. And then G, what does G do? Well, G squares its input and subtracts 5. So I'm actually going to write that. We have the square root of X minus 2 squared minus 5. And when we square the square root of X minus 2, what we get there is technically the absolute value of X minus 2. Why? Well, because the square root of X minus 2 is a strictly positive number. And when you square that, you should still get a strictly positive number. And X minus 2 isn't strictly positive. It depends on the value of X. And then minus 5. All right, so that's what we have here. Now, if you add to that the fact that the domain is all real numbers greater than or equal to 2, meaning X would have never come out of this if X minus 2 were negative, what we see here is since X is greater than or equal to 2, this is just X minus 2 minus 5. So we don't need to worry about the absolute value because X already had to be greater than or equal to 2 to even get here. So X minus 2 has to be positive to get here. So G of F of X is X minus 7 with the added restriction that X has to be greater than or equal to 2. So G of F of X is this function X minus 7, but not all of X minus 7, only the part of X minus 7 where X is greater than or equal to 2. Interesting. So let's move on to our next example. Okay, so in our next example, we have two rational functions. We have F of X is 1 over X, and G of X is 1 over X minus 7. So we're going to do two parts here, F of G of X and its domain, and G of F of X and its domain. And I'm going to go fully to town on the diagram. So for F of G of X, what this means is that you're passing through G first. Well, what does G do? G takes its input, subtracts 7, and takes the reciprocal. So as you all know, you cannot divide by 0. So G says, you can come in, you are welcome here, as long as you do not equal 7. So X says, okay, cool, I won't equal 7. I will come out as 1 over X minus 7. And now I'm going into F. And F says, okay, you are welcome here as long as you are not equal to 0. Okay? But here's the thing, and this is a really important moment. We haven't seen this yet. What is coming into F? What is the input that F is acting on? It's not X. X passed through G, and it came out as 1 over X minus 7, so that's what F is taking as its input. So it's not X that can't be 0, it's 1 over X minus 7 that can't be 0. Well, as it turns out, 1 over X minus 7 cannot be equal to 0. It's not possible to get 0 when you divide 1 by something. So, in fact, this doesn't provide any added restrictions. No added restriction. So, what does F do? Well, F is the reciprocal function. So, let me write it this way. 1 over X minus 7, which is the same as 1 divided by 1 over X minus 7. And dividing by something is the same as multiplying by its reciprocal, which means that this is just X minus 7. And again, it's not X minus 7 in its entirety. It's X minus 7 with the added restriction that X cannot be 7. Because if we go back through our journey, we will see that we would have never made it out of this assembly line if X had been 7. If X was 7, G would have rejected it and the journey would have stopped. So the domain is all real numbers except for 7. For B, well, same exact thing, except this time we start with F. All right, so here we go. F is 1 over X. So F says, all right, here you are. You cannot pass if X is 0. So X cannot be 0. And X says, okay, fine, I won't be 0. I'm going through. And F says, okay, I'll take your reciprocal. Now that X has passed through F, now we move on to G. And G says, you cannot come in as my input if you are 7. Now again, what is coming into G as the input? 1 over X. So 1 over X cannot be 7. Well, when would 1 over X be 7? So what you could do is you could multiply both sides by X. So 7X cannot be equal to 1. So X cannot be equal to 1/7. So you've seen we now have a second restriction. On the one hand, X cannot be 0. On the other hand, X cannot be 1/7. So that's already our domain. But let's walk this through because there's kind of a neat algebraic piece here. So what does G do? It takes the input and subtracts 7 from it. So we get 1 over X minus 7 on the bottom, and then 1 over all of that. So what I'm hoping is happening right now is that bells are ringing. Like, oh, this is a complex fraction. And the way that we've dealt with complex fractions before, you encountered them when we were talking about average rates of change, is we clear the denominators. And to clear the denominator out of the denominator, we need to multiply by X. And of course, you can't just go around multiplying the denominator by X, but not the numerator. So we're going to do both numerator and denominator. And what we get there is X on top. And then on the bottom, we distribute. 1 over X times X is 1. Minus 7X. So let me summarize here. G of F of X is X over 1 minus 7X. And the domain is all real numbers except 1/7 and 0. The 1/7 came from the second pass when it was passing through G. The 0 came from the first pass when it was coming through F. So this gives us some sense of the domain of composition of functions. And I just want to add like one last summary. So summary, I will put it this way. Never forget the inside function. When thinking about domain. So there will come a time that you will no longer draw that little diagram with arrows and boxes and tracing that chain through. There will come a time when you will stop doing that. I hope that time will be a little ways from now. I hope that you will draw these diagrams here, because I think that they make composition much more intuitive. But when you get to that time when you are no longer drawing those diagrams and you're going straight into this sort of algebra and you're looking at the domain, never forget that if your input doesn't satisfy the domain of the inside function, it would have been rejected by that inside function and it would have never made it through the rest of the composition. So that's my reminder. Never forget the inside function when thinking about domain. That's all I have for you. See you later. Bye.